Hi, I'm Schneider and I'm part of the video coding group at the Institut für Nachrichtentechnik RWTH Aachen University in Germany. First of all, let me thank my co-authors Dominik Melem, Maria Meyer and Christian Rolfing for their contributions to this work. I'm going to present the paper about sparse coding-based intraprediction in VVC in the next couple of minutes to you. Let's start with a short motivation for this talk. Intraprediction is the process of predicting a block in an image from reference samples attached to the block. The conventional reference samples, marked in dark gray here, are the samples used in codecs up to 8 GVC for the prediction of the block. Of course, also other samples, the additional reference samples marked in light gray here, could be used for calculating the prediction signal. It's worth to mention that intraprediction is a decisive part of the hybrid video coding scheme, as it's the only option when motion compensation fails or when you start to encode or decode a completely new video sequence. Moreover, the data-driven intraprediction showed improvements over conventional methods in recent years, and this eventually ended in the standardization of matrix-based intraprediction, which became part of the VVC toolset. Therefore, we asked ourselves whether a sparse coding-based method could further improve the intraprediction available in VVC. Let's have a look at the outline for this talk. First of all, I will go briefly through the dictionary learning and sparse coding fundamentals. Afterwards, I will introduce the novel method sparse coding-based intraprediction, or short SCIP. In the third step, we will take a look at the simulation setup and the simulation results. Finally, I will conclude the talk and give an outlook for further research items. To begin with, the general assumption of sparse coding and dictionary learning is that a signal X can be represented sparsely in a dictionary D with a linear combination stored in the coefficient vector alpha. This is only true up to an error epsilon, which models this model error here. In image processing, X is typically a vectorized image patch, but does not need to be a rectangular patch. It could be also some other shape extracted from an image. We will get to that later. The general idea is then to represent the patch by the linear combination of basis patches which come from the dictionary D. Now you can see marked in red here that we only select 4 basis patches, also called atoms, for the representation of the signal X. This is why the solution is sparse. Now the question arises how we can find a suitable dictionary D for allowing for such a representation. This is typically done by solving the dictionary learning problem, which is written as an optimization problem here. This basically optimizes this cost function over the entire training set consisting of n example signals. The cost function includes a term for the L2 norm error of the representation, keeping that small, plus lambda times the L1 norm of the solution alpha, making the solution sparse. Like this, we can find a dictionary suitable for a sparse representation. Once the dictionary is found, we can calculate the sparse codes for arbitrary signals by solving this optimization problem here. It's basically the same, but simply for a single image patch or signal X, and we find the same two error terms, the L2 loss plus lambda times the L1 norm of alpha. It's worth to mention that these optimization problems can be solved by, for example, the online dictionary learning algorithm for the dictionary learning problem and the last algorithm for the sparse coding problem. Both of them are implemented in the SPAMS software, and you will find a link to the software on my references slide in the very end. Let's continue with the description of sparse coding-based intraprediction. First, let's take a look at the core idea from the decoder perspective. The decoder will have available the hatched area, the reference area, and can perform calculations based on that. First of all, this area is vectorized, forming the vector xref representing the reference area. Afterwards, sparse coding is performed on this vector in a dictionary D with a penalty lambda. Of course, the dictionary has to be available at the decoder side and will need to be trained before, but let's cover the training process in a later step in this talk. Out of this sparse coding process, we will find the solution vector alpha and another vector theta, which is the active set of alpha, basically indicating which entries in alpha are non-zero. Further, we divide alpha by its own L1 norm in order to obtain the vector w, which will also be referred to as weights in the following. As we want to sum up this vector w to 1, we further constrained the sparse coding problem such that every single entry in alpha should be either 0 or positive. Otherwise, it would not be ensured that this vector will sum up to 1 after this L1 norm normalization. With the vector w and the vector theta at hand, we can perform multiple linear projections of the reference area onto the block B, which will finally yield our prediction signal. Now, another thing comes into play, namely the set of projection matrices Pi here. These are also trained offline. I will get to the training later. So what we get as final prediction signal is a weighted average of several linear projections of the reference area onto the block B. Another thing to mention is that the reference area in our approach was really limited to the block size and did not exceed the block size, because otherwise we would need to train several more dictionaries and projection matrices P. Not in every case these additional samples are available, and therefore we didn't take this into account. Let's have a look at the training process. Of course, the dictionary can be simply trained by dictionary learning as explained in the very beginning. Now, the image patches are not rectangular anymore, but L-shaped features extracted from a training set such that they match the reference area needed for intraprediction. The training of the projection matrices is a little bit more complicated, and it was performed according to the idea of adjusted anchored neighborhood regression, which showed promising results in the field of dictionary learning based super resolution. In this process, for every dictionary atom di, the training set is searched for the nn nearest neighbors, and this yields a neighborhood nfi and a corresponding neighborhood in the label space nli. With these neighborhoods, the projection matrices can be calculated by the formula 4 here. The formula will not be detailed here. You can find details in the paper, but it's important to mention that we introduce another penalty here, which makes sure that this matrix is not becoming singular and the matrix inversion can really be performed. Let's take another look at the entire scheme. You can see the training process, which is performed offline in the upper part, and the prediction process in the lower part. The final question which needs to be answered is what needs to be transmitted to the decoder side in this scheme. And this is only a single flag indicating whether this method should be used or not. We can infer the weights W and the active set theta from the sparse codes found in the reference area. So therefore, there is no need to transmit the weights. The only thing is to indicate that this method should be applied. Now let's have a look how prediction signals obtained by SCIP could look like. The figure on the left visualizes an example dictionary with 64 L-shaped atoms and corresponding projections di times di for 8x8 blocks. The atoms are separated by this thin black line here from the projection in the lower right corner. Therefore, you can see that an atom having this structure is projected onto the block like given here in the lower right corner. We can directly observe that the signal, the prediction signal, is smoothed out when the samples are lying closer to the lower right corner, as the prediction becomes more inaccurate on average, and therefore in a least square sense makes sense to smooth it out. You can see directional structures which are predicted like this with this approach, but we could also see that even circular structures could be predicted like this. Let me get to the simulation setup and corresponding results. First of all, the implementation was based on the VTM93 reference software, and simulations for all intra and random access coding were performed according to the common testing conditions of JVAT. SCIP was only applied for the Luma component, as the Chroma components were assumed to be handled by the cross-component linear model in VVC. The combination of intra-subpartitioning and SCIP was not allowed for implementation reasons. Further, SCIP was allowed and fully RD tested for block sizes up to 32 by 32 pixels. The table below here shows the parameterization of the SCIP scheme. The number of dictionary atoms were chosen to be 512, and the neighborhood size for the anchored neighborhood regression was chosen to be 2048. The sparse coding penalty lambda was set to 0.1, and the regularization lambda plus for calculating the projection matrices was chosen according to the block size in order to prevent the matrix inversion to become infeasible due to a singular matrix. The table on the left shows the simulation results in terms of Biontech delta rate savings and usage percentages of SCIP. The usage percentage was calculated on the per pixel basis. You can see that a consistent gain for the JVAT sequences is observed. For the all-intra coding scenario, we observe on average 0.26% of rate savings, and for random access 0.1% of rate savings. Of course, the gain for all-intra is larger than for random access, as all-intra uses simply way more intra-prediction than random access. The peak gain is observed for the foot market sequence with 0.6% of rate savings, and also the usage percentage is highest in that case. Moreover, the best performance is observed for the class A sequences, where almost 0.4% of rate could be saved. Let me conclude and provide an outlook. In conclusion, SCIP shows a consistent gain over VVC and a remarkable usage percentage. In particular, for the higher resolution sequences, so the class A sequences, higher gains are observed. This could lead to the conclusion that SCIP could be beneficial also for still image coding, where the resolutions are even higher in comparison to the class A sequences. As an outlook, I want to state that the reference area was limited to the block size and not exceeded it, so therefore also samples at the bottom left or top right could be used for SCIP as well, and this could even lead to a better performance. Moreover, the assessment and potentially even the reduction of the complexity of this method was not addressed in this paper. Therefore, this is also open as a further research item. Lastly, let me show my literature, and I will hold on for a second so that you can stop the video if you like. So that's it from my side. If you have any questions, feel free to ask them. I will be happy to answer them in the Q&A session.